Hey, friends, there are many things that Jesus is. There are also many other things that he's not. One of the things that Jesus is not is a quitter. It's not in his vocabulary, actually. And so Paul could write to the Philippians that he who began a good work in you will carry it on to completion until the day of Christ Jesus. I'm a work in progress. God isn't finished with me yet, and that's a very good thing. I hope you are too. And just know that someday we will be the people that God intended and created us to be. Jesus doesn't quit. This lesson is on chapter 14, the second part. So we're in the latter part of the 19th century. And here I want to talk about three more people: gentlemen, Weierstrass, Riemann, and Poincaré, and then deal with what Eves calls the arithmetization of analysis. Finally, explain why this is probably a pretty good place to stop the course, because we would have to get into the 20th century, and 20th century mathematics is a whole nother animal to describe. Weierstrass, unusual gentleman, had a first career for several decades as a secondary school teacher and then a second career as a researcher, university professor. Many of the people that we've talked about have been brilliant researchers, but not very good at teaching and writing. Weierstrass was good at both, and one can presume that that may have been because of his prior experience of years and years of teaching. Some of the things that Weierstrass worked on, they were mostly in analysis, by the way. He gave what we now call our definition of a continuous function. He proved the intermediate value theorem. You study in Calc 1, remember that says that a continuous function can't go from f of a to f of b without going through all of the values in between. He gave an example of a continuous but nowhere differentiable function. So I think it's an accident that this function, the graph of this function, actually happens to look like a W. It's Weierstrass's function. But the important thing is that this function is defined in a tricky way so that the graph is continuous. You could theoretically trace it all along here without lifting up your pencil. But at nowhere is it differentiable. If you zoom in on any section of the graph, in fact, you see that it's jagged everywhere. So just like the absolute value function doesn't have a derivative at the origin, this function doesn't have a derivative anywhere. And this made people rethink what it meant to even be a function. People would have, in Weierstrass's time at the beginning of his career, would have said, no, that can't happen. Every function that's smooth enough to be continuous is surely going to have a derivative at most points. Not true. Weierstrass's most important work was in complex functions. We know that this equation is a true statement about real numbers. If you plug in any real number for z and crank out the value of this power series, then this is an equality. And Weierstrass had great success in saying, well, what about if we replace the real number with a complex number? So we know what, say, e to the fourth power is, but how about e to the 3 plus 4i? What in the world does that mean? And he said, well, you take the power series that applies for real numbers and you just stuff in a complex number and see what you get. And indeed you do in most cases. Riemann, notice, only lived 40 years, but accomplished a lot in that time. The calculus that we study today includes integrals, and in fact, it includes what mathematicians call the Riemann integral. We won't go into anything else, but there are other kinds of integrals, other ways of doing integration that you would study in a graduate level class. So Riemann integrals involve this idea of vertical rectangles and using upper sums and lower sums and convergence and so on. You know about that. Riemann also worked in geometry, and today there are geometries known as Riemannian geometries. Here's a flavor of the idea he was trying to capture. Here's a plane. It's two-dimensional. I can think of it as a piece of paper with negligible thickness, so it's two-dimensional. And on it, I can draw triangles and things like that and talk about the shortest distance between 2 points, etc. Or we could do the same thing on the surface of a sphere, which is also two-dimensional, and something different happens, right? The shape of triangles is different, and when we join 2 points, we now no longer mean a quote-unquote straight line, but we mean an arc of a great circle. Or on a saddle, which is a surface of negative curvature, we can, and this is hyperbolic geometry, we can draw triangles and talk about the shortest distance between 2 points. The shortest path between 2 points is called a geodesic, by the way. So Riemann said, well, what happens if I take this piece of paper and just wad it up? Then I get something like this, but it's still a two-dimensional surface, even though it's all rolled up. And now I want to talk about getting from point G to point H, say, but I have to stay on the surface of the paper. Now, how can I describe what a line looks like in that situation? It probably is the case that the shortest path between 2 points is to follow some really jagged trajectory here. And how can we measure distances and define what it means to be the shortest distance and so on? That's Riemannian geometry, and it turned out 40 years later that that's exactly what Einstein needed to develop his theory of relativity. The general theory of relativity is built on Riemannian geometry. Riemann also made a hypothesis called the Riemann hypothesis today. It still is a hypothesis. It hasn't been proven. And in fact, it's the most famous unproven hypothesis or conjecture in mathematics today. That used to be Fermat's last theorem, but when that was proven in 1993, the Riemann hypothesis became the most famous unproven conjecture. It's a little hard to describe, so let me just say that in mathematics there is something called the Riemann zeta function. And when we take the zeta function and set it equal to 0 and start looking for the roots or zeros of this Riemann zeta function, people notice that, well, there are a few roots at predictable places. By the way, this is the complex plane. So here is the real axis, and here is the imaginary axis. And the Riemann zeta function has some roots that are negative real numbers. We know about those. But it also has some complex roots. And to date, every complex root that has been found has line on this line, which has real part 1/2. So the conjecture or hypothesis is that all complex zeros of this function have real part exactly 1/2. It's been proven that all the complex zeros have a real part that's approximately 1/2. So, and by approximately, we mean really, really, really close. People have shown that the real part of these roots can't be very much different than 1/2. But to say that they are exactly equal to 1/2 is a different question that has not yet been proven. Most mathematicians think it is true. Poincaré was called the last universalist, meaning that he was perhaps the last mathematician who could understand pretty much any topic or any subject area in mathematics. Or some people would say maybe that was Carl Gauss a little earlier. At any rate, it doesn't happen anymore that people are able to understand all branches of mathematics. Poincaré was very productive. He wrote over 500 math papers, and here's something kind of new. He also wrote expository papers for the general public so that they could in some sense, understand the new mathematics that was being developed. So this could be something like the, I don't know, Khan Academy or number file of the day. They were very popular and very well done. What do we mean by expository paper? Well, in that case, we're not trying to explain new mathematics that we have developed ourselves. We're trying to explain mathematics somebody else has developed, but for the general public. So without using so many technical ideas. Poincaré was also a physicist as well as a mathematician, and he described invariant forms of many laws of physics. So we talked earlier about the fact that we could use rectangular coordinates or polar coordinates or spherical coordinates or cylindrical coordinates and so on. And Poincaré realized that the coordinate system shouldn't make any difference in what was actually true or not. And so he was able to formulate many of the laws of physics in ways that didn't change when you changed coordinate systems. Poincaré was also one of the founders of dynamical systems and chaos. You could think about maybe here's a double star and there's a planet rotating around the double star. And what kind of path does it take over time as it rotates? And he was able to show that in certain situations, the path is highly interesting geometrically, which we now call chaos. And maybe most importantly of all, Poincaré was one of the founders of the branch of mathematics that we now call topology, which we won't get into, but a huge and important branch of mathematics that overlaps with lots of others. If you had been around a little earlier in life, maybe you could have taken a shot at proving the so-called Poincaré conjecture, but it was finally proven about 100 years after Poincaré in 2003. Now let's talk about this arithmetization of analysis. It stemmed out of the fact that mathematicians realized that they needed to make the field of analysis more rigorous. So we've been discussing that idea or that topic for a while back when we talked about Lagrange. He was perhaps the first person to realize that this needed to be done, but really wasn't able to do it himself. Cauchy in the early 1800s accomplished quite a bit. He began giving rigorous proofs in analysis. He was the person to propose the epsilon delta definition of a limit and the fact that an integral could be defined as the limit of sums and things like that. And then the people that we just talked about, at least Weierstrass and Riemann and others, pushed this through, this program of arithmetization and making things rigorous, and were pretty much successful. So what it turned out needed to happen was that we needed to step back and talk about what we meant by the real numbers. As soon as we were able, mathematicians were able to rigorously explain what they meant by the real numbers, then concepts of analysis that had been elusive fell into place. So the arithmetization of analysis means that analysis is chased back, reduced to talking about questions dealing with arithmetic, really, the real numbers. But let me point out that the real numbers are more complicated than what you possibly have thought to this point. Most of us grow up and think of the real numbers as points on a number line, the real number line. But if you start asking more probing questions, you run into problems. So like square root of 2 is a real number, and we put it on the number line here. But I can ask, well, what do you mean? Why does it go there? And you say, well, that's the distance from the origin. And I say, well, what do you mean by distance? And you say, well, I have a ruler or something to measure lengths, and I just come out here that far and mark on it, and there's square root of 2. And I'd say, well, where'd the ruler come from? Oh, well, that's another real number line. And so now we're definition chasing. You can't really talk about where the points are until you have a concept of distance, and you can't talk about distance until you really have the real numbers in hand. It turns out that it's better to actually derive the real numbers from the rational numbers. So for example, a modern mathematician would say, what do I mean by square root of 2? Well, let me take the rational number 1, and the rational number 1.4, oops, I skipped one, and then rational number 1.41, 1.414, and so on. These are all rational numbers, so we know what they mean. And then we can talk about taking the limit of this sequence, and that the limit might be what we mean by the number square root of 2. In real analysis, we talk about, well, how do we know that this sequence has a limit at all? Finally, let's talk about 20th century mathematics just a little bit. The difficulty is that describing 20th century mathematics to a layperson, somebody who's not very familiar with mathematics, is increasingly difficult as time goes by for several reasons. One of which is a very high level of abstraction and generalization. So, for example, you might ask a research mathematician today what he's working on, and he tells you, and then you ask, well, what are some of its applications? What is it good for? And because the work is so far removed from any quote unquote real life application, he has great difficulty in explaining it. And in fact, you may get a little indignant. It's like, what do you mean, what application? Why should my math have application? I'm just doing it because I enjoy doing it and because it's true. Another difficulty in explaining mathematics today is that many of the problems, most of the problems, have such a high level of prerequisite knowledge. We've been seeing that for several hundred years now, even in the 17th and 18th and 19th centuries. It was hard to describe what some of these mathematicians were working on because we haven't really had the background knowledge needed to understand it. A third reason is the blurring of lines between so-called branches of mathematics. I'll talk more about that in just a moment. And finally, the pace of discovery has gotten so fast that if you write a book about mathematics and its classification and so on, the book is out of date before you finish it. Now, regarding the branches of mathematics, mathematicians are organizers, right? We love to classify things. We like to classify mathematics itself, at least some of us do. So one of the analogies that's often been used is the idea of a tree. Like geometry and algebra are really important to the rest of mathematics, and so we call that the trunk, and they hold everything else up, where we have things like game theory and probability and group theory and so on. Well, over time, people have realized that algebra and geometry this may not be the right thing to put in the trunk. And in any case, whenever I draw a picture like this, I'm making sort of the implicit claim that topology and, say, graph theory must not have much to do with each other because they're far apart on the tree. When in fact, many mathematicians would say that graph theory is just a part of topology. No matter where I put these things, they're not completely illustrative of where things really are and the relationships that really exist. So here's another picture, so small it's hard to read, but maybe better than a tree, at least, would be to try some kind of Venn diagram. So here, this set of authors has drawn a bubble for analysis and for algebra and topology, logic, and discrete math. And these bubbles overlap, and we get branches of mathematics like algebraic geometry and so on. Interesting to note that geometry itself, in the classical Greek sense, has now been demoted to sort of a subfield of other branches of math. But we still have the same difficulty here. Discrete math, some people would say, is part of topology. And so it becomes virtually impossible to do any sort of really accurate picture like this to describe 20th century mathematics. And we will stop there.